And he's a great professor, and he taught me a lot that I know. So let's just clap for him. What's his name? I don't know. His name is Michael Mann. He is going to be talking about TS-Raster, which is a Python package for doing time series analysis. Something like that. And he's going to talk about it in the context of wildfires. And I'm going to be looking at Dan, because this is his computer, and he knows how to set it up. Yeah, great. I'll give him lectures before. Hey guys! How's it going? All right. This is the first time I've given a lecture with a beer in my hand. So, cheers to that. Thank you. I guess I should do this more often. So today I am going to try to not bore you. I am very much a technical weeds kind of guy, and I will try not to get too weedy on you. What I want to talk to you about is California burning. I think that we're all pretty familiar with what's going on in California right now. Huge fires. It seems all kind of apocalyptic. The good news is that we caused all of these problems, and the bad news is that we can actually, well, we have to solve them, right? Basically, what my main argument is that we've created a situation that's essentially untenable, largely by removing wildfire from a landscape that used to burn all the time. And I'm going to try to convince you of that. And then I'm going to show you my little nifty tool that I worked with Eddie Adonu over here. Raise your hand, Eddie. Come on. Don't be shy. Everybody should hire that guy if you can get your hands on him. Okay, so take a look at the Bear Creek Guard Station 1915. Look at it in 2002. And let's just toggle back and forth and appreciate the differences there. So we go from about 30 to 60 trees per acre to about 400 trees per acre, and something close to, whatever, 100 years. So we've removed fire from the landscape. All this stuff wants to burn, will burn, and there's not all that much we can do about it. So we're used to sort of seeing stuff like this. So we see this increasing trend of area burned in California over time, and now the awe slide. Some historical context. Look at the x-axis there, 1800s. So pre-colonial times, we have basically completely removed wildfire from the landscape. This is a fire-adapted landscape that is supposed to burn most areas between, I don't know, 10 to maybe 80 years. I guess the deserts will never burn, so that's infinite. But not all that many people live in the deserts. So this is the context. I'm not saying we're going to get back to that anytime soon, but this stuff is inevitable, right? We can only put it off for so long. The hard part for me is how to model this. So I'm helping helping FRAP, which is the California Fire Resources Assessment Board, try to update their wildfire forecasting models. And extracting time series data and trying to make some prediction on it is the thing that has been the bane of my existence since I started doing any of this work. I used to sort of cobble together a script, and anytime I tried to use it on something else, it would break. It was a complete nightmare. So with Eddie, I've been working on a system that essentially you say, hey, here's my folder of time series rasters, so this can be something like greenness over time or precipitation or temperature, and you say, hey, give me a bunch of different time series metrics from it, and I'm going to use that to pass it forward into my machine learning models. I've been using it in Ethiopia to do crop loss detection early season. It's working really well in that context. It's working really well with wildfires, I'll show you. But there's like a million different things that you're trying to predict a particular event at a particular time and place. The hard piece for me has always been, okay, if you have like precipitation, how do you extract the features that are meaningful for a given year? Right? Is it the maximum precipitation that matters? Or is it the minimum? Or is it the longest time below the mean? Or is it the Fourier transform? Or is it God knows what? So what we've done is develop a system that can very quickly and very easily extract up to 1,200 different time series characteristics. And then you can just feed that forward into your machine learning models. And to give some sort of visual idea of how we're trying to use this, this is an example of, this is just wildfires, I think from 2013 to 2016. And here are some of the time series features for those same areas. And it might be sudden changes in plant productivity. AT is an indicator of plant productivity. Maybe it's these things that are driving wildfire events in grassland areas. Or maybe it's sort of the average productivity of an area, or the dryness, or maybe it's one of any number of things that happen. Right? And what drives wildfire in a grassland is going to be completely different than what drives it in a shrubland. And luckily we have machine learning now that can help us differentiate those things in a meaningful way. So in the end, we're spitting out models, and sorry about my ArcGIS crappy map here. It's embarrassing. I have a postdoc who's now doing stuff in ArcMap, apparently. It's a little sad. It makes me want to weep. And it's not even Arc Pro. Sorry, a lot of my students now work for ESRI, so sorry about that. Anyways, in the end, the good news is that we're able to make these predictions much faster, much earlier in the season, with pretty high reliability. So the preliminary models, I'm sort of hesitant to show you the final stuff because we're nowhere near there yet, but we're out of sample, we're basically estimating that we can get about 50% of fire pixels completely out of sample, which is pretty freaking good. In my world, and that's about all I have. So sorry, I took you from high level to something pretty nerdy, but I'm a nerd. Thanks, guys.
Yeah. Do you have any questions?
Yeah, a quick question about the slide you said early on with the sort of rapid decline in total burn. Is that for just California, or is that a national?
Yeah, this is just California.
So my question about that is, like, obviously the East Coast, saw a lot of clear cutting during this period. Did California have safe clear cutting? Because then, of course, like, the total burn acreage for the whole state would go down.
So one of the interesting things is that, and this is sort of an argued fact here. I should say that, but essentially, the Native Americans used to use wildfire as a tool to clear landscapes, make it more to essentially make it better habitat for animals, or for hunting ground and all that kind of stuff. So some of this stuff is definitely human introduced. But the ecosystems that built around it are fire adapted, right? So things like chaparral are essentially designed to explode in flames every 5 to 15 years, more or less. So a lot of the landscapes that Californians have chosen to build in, which was a terrible idea, are now getting what was sort of inevitably going to happen. Yeah.
How does climate change tie into this? Because there was a lot more burning in the past, but now there's more climate change. How does that change how the environment might be more inclined or less inclined to burn?
Yeah, and you're definitely seeing climate change signals in this, right? It's you have essentially a lot of standing fuels that now are suddenly becoming drier and drier. So all it takes is that one match, and there's more humans on the landscape. So that one match is much more frequent. So essentially fires get bigger, get more out of control, there's more of them. That's sort of how it plays. But I do want to emphasize that a lot of natural disasters are human problems, right? Like, we removed fire from the landscape, now we have to pay that price, and we moved into that landscape. If nobody lived there, we could just let it burn. Like, fine, okay, it's supposed to burn, we let it burn, not a problem. So there is this really interesting mix of climate change and land use change that's really made this the worst possible situation.
Are you looking at all other human factors like utilities and?
Yeah, we have power lines. I have a housing forecast model that I did a while ago to forecast where people will live. Yeah, that's definitely an emphasis.
So it's like 16 of the 18 fires apparently were started by some
PG&E.
PG&E or
Again.
or Southern California Edison. I mean, it's
Yeah, the utilities are playing a huge role in this, and yeah, it's
but
a lot of, I think it's something like 75 to 80% of fires are started by humans in California, and it's surprising none of those are done intentionally.
Last question. Go for it, though.
So, part of my ignorance here about that 50% that you were talking about that you've gotten to be successful.
Yep.
Is that actionable for people fighting these wildfires in California, or are you trying to get higher than that?
So my modeling is very different than folks that are actually fighting a particular wildfire. So those are mechanistic models where they're interested in how a particular fire spreads across the landscape with wind and weather and rainfall and all that kind of stuff. What I'm interested in is what can we say about 20 years from now and the risk, the probability that a fire will happen on the landscape. What will happen 100 years from now? So they're related but also very different questions. Yeah. Thanks, guys.